part of the presentation. We will start with the alternative or comparison system done by Drago.
Time to start!
Ding dong. Okay. What I'm going to talk about is an alternative to the whole pipeline from Czech to English, and more specifically, I'm going to discuss how to convert the automatically generated text-to-grammatical representation from the Wall Street Journal feedback into surface English. So this is essentially part of the generation part of the pipeline. And what makes it interesting is that because the text-to-grammatical representation is also used in the machine translation stage, you have reasons to believe that this would be a viable approach for generation for machine translation as well. And in fact, we have performed experiments with both generated text from English and from Czech. So let's look at an example. Suppose that this is the sentence that you want to generate. Alan Spoon recently named music friend and said music's ad rates would increase 5% in January. This is a real sentence from the Wall Street Journal, and I'm going to show you the corresponding text-to-grammatical representation for this sentence. So this is what you have. Remember, the text-to-grammatical is a dependency framework, and you have the root, the predicate, which is say, and then you have a certain number of so-called functors in the Python school. Those correspond to the deep semantic and syntactic roles, such as patient, position, two actors in this case, and so on. So the task of my system was to produce this sort of sentences from this sort of input. So let's look at the TR in a little bit more detail. You can see that some words appear there, for example, increase, rate, Newsweek, which are the so-called autosemantic words which bear the most important content of the sentence. There are many words are missing, for example, prepositions, inflections are missing, and so on. Let me show you an example here. Suppose this is the sentence. Those are all the words that appear in the text-to-grammatical tree in order, that first search, that first traversal. And this is the sentence that you actually want to generate. As you can see, many of those words, the ones that are shown in white, can directly be transferred to the output. However, there's some words, like the red and the purple ones here, which have to be inflected. So say has to become said, and rate has to become rates. And then finally, you have words which are which don't appear in the text-to-grammatical lemma structure at all. For example, the prepositions and the possessive apostrophe s. So what I try to do is this. Look at the different sort of architectures that exist for generation and see what is the most appropriate architecture for this sort of generation. So at one extreme are the generation systems which are purely statistical. So those are the decisions that at each node have to decide how to order the internal nodes, how to do word choice, how to do the final word ordering at the constituent of the surface level. And then at the other extreme are the systems which use predefined manual grammars to produce output which already has an idea of the different semantic constituents. So at one extreme is magenta, so this is the system that has been described so far. It is based on three substitution grammars and based on alignment between two different representations. In one case, it's text-to-grammatical to analytical level, but it can also be, for example, text-to-grammatical to context-free, parse-free, and so on. Then rule-based systems such as FOF and Surge, which were developed at Columbia in the early 90s, and KPML, the John Bateman system, and a few others, are essentially rely on handwritten rules. So you have a rule that says that, for example, in a certain type of sentence, for example, if the voice is active, then the internal agent comes in a specific position, and so on. Now, hybrid approaches have become very popular in the last few years, starting from the work by Knight and Hadzi-Vasilova in '95, which was nitrogen systems. The basic idea there is that you have many possible ways to represent the same output. So for example, with or without a preposition in a specific location, with a certain inflection or with another inflection, with a specific word order or a different word order. Once you generate the output in the form of a forest, you use an n-gram ranking model to decide, well, is this string more likely than that string? So a more recent implementation of this idea was found in Irene Monkfield's thesis work. Again, a very nice piece of work this year, finally finished, the halogen system. So another system that has some sort of cabinet approach was the Fergus system by Srini Bangalore and Owen Ambo from AT&T a couple of years ago. Now, we're trying to situate our system Argent, which is, again, a color name. It means analytical representation generation for translation, and try to situate it with respect to the other system. Let me first show you what FOF can do. So the idea is, here's this. Instead of making all the decisions using a statistical approach, and also instead of using a purely manually written grammar, you want to have the best of both worlds. So you use the manually written grammar to generate, for example, the top level constituents or some specific constituents at the lower level, for example, noun phrases and conjunctions and oppositions. And then how to actually produce the rules is done on a statistical basis. So here's what a system such as FOF and Search can do for you. It can, for example, map the thematic structure for FOF. For example, FOF is a functional unification formula. It's like a holiday and a kind of approach whereby you have different processes with different participants, affected roles, and so on. So if you have this in your input, then FOF can produce the right syntactic roles. Then you can also do syntactic paraphrasing and alternations. For example, you can do dative move, like John gave Mary a book, John gave a book to Mary. You can have passive constructions and so on. And so there's a large list of things that a grammar like this can do for you, provided that you can give it in the input the right control structure. For example, if I tell the system, change the voice from active to passive, it's going to do all the necessary rearrangements of the trees for me. But it doesn't know when to actually decide to do this. So this is what we can do with FOF and Search. But what we cannot do is convert the dependency structure at the tectogrammatical level to a phrase structure. You don't have control for syntactic paraphrase. You don't have control for lexical features, for example, how to deal with tense, aspect, mood, and so on. You don't choose determiners, and also the built-in grammar in FOF is very nice, but it's not robust. This definitely doesn't scale up to the current sentences that you can have in the Wall Street Journal, which is where we're starting. So here's an example of an input structure to FOF. So you have to specify all the things. For example, what is the process, what is the circumstantial module. You have a participants module which contains affected, agent, and so on. In this case, agent is an opposition, and so on. So in your input, however, you have a totally different structure. You have a dependency tree, a predicate. Here you have an opposition. You have the heads here of the two actors. One is the name of the person, Spoon, and then here name, which is a past participle, which forms the head of this entire part of the opposition. You also have here patient, said that, something will increase, and so on, which is all dependent on the root node here, say. And this is the equivalent to the previous slide in FOF representation. So once I get to this stage, then FOF will do everything for me. It will decide word order, it will decide on the inflections, it will decide how to insert prepositions, and so on. As long as it has, again, the right control structure. So some of those decisions are very easy to do. For example, to map the top level predicate of the sentence into the lex of the process, which is the equivalent to the main predicate in the functional unification formalism, is straightforward. Similarly, it's very straightforward to map proper nouns or names of people of all kinds, like Newsweek, just maps as Newsweek. In this case, the path to Newsweek is here, it's the actor of the patient. Whereas here, it has to get mapped to the participant, which has an agent and then the possessor. And this APP here is a pertinence functor, which is a Pragian term for possessor. Okay, so those are the easy decisions. But how do you deal with the hard decisions? If in your input you have something like T1 January, well, syntactically realize this, you have two options. One is to do it on some sort of a word, bag of words approach, whereby you start with the word January, and then you end up with in January, by just inserting a word without paying attention to the internal structure of this node. Or you can do it in a more syntactically accurate way by positing that this T1 is actually circumstantial, which is straightforward to tell, because T1 can only be a circumstantial, but then this circumstantial is actually represented as a prepositional phrase with a head in. And then the noun phrase itself has a lex or lexical component, January. And this whole thing is a prepositional phrase. So this is something that you cannot do in a very straightforward way. And that's why you have to have a manually or automatically produced tool to do this. Another example is the top level of predicate here is somebody said that something increased. Well, to actually represent this in the surface level, you have to be able to map this into some sort of embedded clause. Like here, you have the process is an object clause headed by that. So this is the equivalentization. In your lexicon, you can have a rule that says that whatever a predicate is headed by say, in the corresponding file structure, you're going to have an object clause headed by that. And this is like the head of the verb of the object clause is going to be the head of the predicate. Okay, so what I have to do is write a translator from technogrammatical representation to FOC, which can be used here for generation and for machine translation, but can also be used for things like question answering or text summarization using different inputs and different outputs. So the idea was to write the high coverage rules first. So what I have is essentially a mixed initiative system whereby my system tells me what kind of rule I need to write next based on its frequency and based on how it corresponds to the rules that I have already written. So only with something on the order of 400 or 450 rules in the grammar, like 10 pages of grammar, you can produce a very large coverage output. And I'm going to show you some numbers on the next slide. Now, the translation could be done even better, even faster, if you had some online training data between technogrammatical trees and function unification trees, which would be equivalent to what Jason was talking about in the AR to TR alignment. However, we don't have such data. So therefore, this is out of the question, although there are some ways to actually bootstrap, which I'm going to talk about. Okay, very quickly, there are 4 types of rules I'm using the taxonomy that Lansfield's thesis mentioned. You have recasting rules, ordering, filling, and morphing, where morphing is the morphological rules. Recasting is rules that tell you, for example, that a noun phrase, the noun, for example, has to become the head of the noun phrase, of the prepositional phrase, and so on. There are 3 modules which are part of the translator. The top level, which deals with the known technogrammatical functors at the predicate level, such as agent and patient and so on. Then there is a recursive module which steps down through the constituents and decides which of the different components have to be realized as a verb phrase, as a noun phrase, as a prepositional phrase, and so on. And then you have a bottom level grammar which deals with the chunks at the very bottom, where you have, for example, a noun phrase headed by a noun with a certain number of restrictors. For example, add rates, like in the previous example. The add rates, the rates is the head. Okay, so some evaluation. We have tested Arjan. This is on the dev test. I just got the final numbers for the eval test, which is exactly the same. We have 236 out of 239. So our eval test has 239 cents, which is approximately the same, so only 3 were not covered by the system. Whereas Halogen comparably achieved 80% coverage. Now, I must say that those numbers are not exactly comparable. They are in some way because they're both in the Wall Street Journal type of text. However, ours is on a small set of it rather than the entire section 21 or whatever Irene was using. Now, speed-wise, Arjan is very quick. Right now we have about 1.4 to 2.9 seconds per sentence. Now, this is a totally different kind of evaluation machine, but I thought it's worth mentioning, especially considering that comparable systems achieve 1 minute per sentence. And Blue Score is going to come in the final comparison of the different systems. Future work, to complete the grammar, we need to improve the coverage, especially dealing with errors. Now, remember that there are 3 places where errors can be input into our system. One is in the translation process, one is in the assignment of functors, and one is there are several different places that can embed errors. So for example, we have cases where the input contains a predicate and 3 actors, or 3 patients, which is syntactically inaccurate. So we don't expect this to be in the grammar, but you would expect to have an opposition or conjunction as a head of all those things. And this actually happens in the data, and you have to be able to deal with it. So, okay, so there's some things which we didn't use in the grammar, which can be used to extend its coverage. For example, deal with certain low-level grammar themes, such as degree of comparison, set mode, verb mode, for example, interrogative sentences for imperative verbs, and so on. Grammar induction is essentially the idea is in the absence of FOF trees, so that you can learn the alignment from TR to FOF, but in the presence of the actual output of FOF, you can imagine some sort of a model whereby the FOF tree is the hidden representation, and you actually have to infer it from the existing tectogrammatical tree and the surface sentence itself, which is also known. And what makes this task probably easier than you may imagine is that once you come up with a hypothesized FOF tree, you can run it through FOF and produce the output, and then you can score it using the blue metric or the NIST metric and decide how well this particular transformation works. And now, one thing that can be done is to integrate with the rest of the system, whereby you would learn some small tree transformations. For example, how do you map from a T1 to a prepositional phrase headed by in and with the month as the head of the noun. Okay, that's my part.
Okay, thank you. So now, finally, we are coming to the numbers. So let me say first what we have actually achieved from what you have heard about here. And in fact, we haven't finished the system as we wanted to finish it, but that's kind of usually the case at these workshops. But let me do it one by one. So the initial tools have been done before the workshop, and some of them are actually as old as the workshop 98, and some of them are developed independently of these workshops. And we have also used for the transfer the PISA system developed at 99 and some other stuff that was developed prior to this workshop. We have the rule-based parser, but we do not have the statistical parser. So obviously the translation results, that means the results for the so-called input 4, which is all the way from Czech, will be bad because they only can use the old rule-based system. For the input 3, that was the thing Owen was talking about, we actually haven't integrated that into the training phase, but we could now because it was like done, we will be able to do it in a couple of days, but we only have some partial results on the input itself that uses the model trained on a different data. For the actual tree-to-tree transformation system, we have the aligner and decoder running. That was Jason's part. We have the litter tree model. That was my part, but it uses the simple smoothing I talked about, and so that's kind of it works. The biggest drawback we got was that we were unable to integrate the real proposer, the one that will be actually trained on the data. So in fact, what we are using in the system I will report on is a proposer that's actually just a couple of lines of code that simulates some of the things that we would expect from the real proposer to do. So we are only dealing with the determiner insertion, and for every noun we insert 5 most frequent English prepositions. So the proposer is actually very dumb at this point. And I will show how it affects the results also. The preposition classifier was done and evaluated, as you have seen. But again, it was not really integrated into the system because it has to cooperate with the proposer. And since we do not have the proposer, there was actually no way to put it at this point. But other than that, the rest of the system was fully implemented. So the work order model we actually had at the very beginning of the workshop, and we were able to improve it a little bit. We developed the comma insertion, and that's part of the system. And we have the English morphology running, and it's also part of the system. And then we have a Drago system. It's now also capable of running. So again, let me repeat before I show the actual numbers that we have used the blue score. We had 5 reference translations. I think this is one of the good results of the workshop because these were actually very expensive to produce. Even though it's only about 500 sentences, it costs about $10,000 to do those. And I think they should be reused, and of course they will be available for other purposes. So we have the Czech original and 5 English variants of those sentences. Now we have these 4 inputs we already talked about at the beginning. We have the automatically derived English TR. We have the manual annotation. We have the enhanced English technogrammatic level, and then we have the complete system that goes from Czech all the way to the English TR. And all these 4 inputs were evaluated, not all of them on all the tracks, but we have some results for all 4, and then we have the hybrid system that runs on well, we have both systems and some numbers on all 4. We also did what we call the upper estimate. Since we had those 5 reference translations, it was a natural question, how well people do against each other, right? So we have 5 translations, and we always took one out and then evaluate that as the output of the system against the 4 others. And in fact, all our evaluation was done like that, because of course, if you add a reference translation, your numbers go up. So that would not be fair to compare our system against 5 translations and the people only against 4. So we always did it against all 4 tuples of the translation and then made an average. So the average blue score on the manual translation is 0.556. So it gives you an idea that even though the blue score goes from 0 to 1, so even if you evaluate a person that's supposedly a reference translation against some other translations, the score is hit quite a lot. So most of the blue scores are kind of in the lower half of the scale. So here are the results. Now, the input one, which is the automatic English TR, is supposed to be the easiest case, because actually we went from English to deep English and then back to the surface English. What we did, we computed for all the data a baseline. Now, what is the baseline? That was done by Terry, actually. We just didn't have time for him to present his part. But he developed a baseline system. The baseline works like this. It takes all the nodes from the dectogrammatic representation, and remember those nodes contain the lemmas, which is the uninflected base form, plus some extra nodes like the general subject and stuff like that. And he takes the lemmas and just prints them out and ignores the nodes that are non-lemma nodes. Okay? So no inflections, no insertions of prepositions or anything like that, just prints out the lemmas. Now there are two methods how to do the baseline system. One is that he uses the original order that's in the file with the trees. But in some cases, that would not be the fair baseline, because obviously when you go from English to dectogrammatic English automatically, that preserves the word order. So that would give us a too high baseline. So for the automatically derived data from English, we have used a randomized baseline, meaning that he simply moved the words in a random order and then output the lemmas as I said before. So for the T1 test, we use the randomized baseline, and that's 0.04. Obviously, it's very small because the unigrams are quite good, but since you have random order, the order is really bad. And these are the 2 numbers on the dev test and the eval test. Now, the statistical system, that's what we call preliminary agenda, got 0.253 on the dev test, and this is actually the right number. This is 0.244 in the evaluation data. So the conclusion from the input 1 test is that we can actually restore the English about halfway to the people performance. Of course, again, this is randomized. This is also kind of based on randomized order, because the word order module actually tries all possibilities. So it doesn't pay any attention to the original word order. So these numbers are fairly comparable. Now, for the hybrid system done by Drago, the number on the input one was lower and was about 0.15, 0.14. Now, for the manual English DR, and this starts to be a fair, much more telling test. The manual English DR has a defined word order, namely the deep word order. So for this test, we could actually use that order because that's independent. It's not independent in the mathematical sense, but theoretically it's independent of the surface word order. The deep word order is defined by the discourse structure, so that new things go left and old things, the things that you mentioned, in the context go left and the new things go to the right. So it doesn't have to correspond to the surface walk volume. Therefore, for the baseline, we didn't have to randomize. We could use the deport volume. So therefore, the baseline is much higher than in the previous case. It's 0.16 on the evaluation data. And kind of not surprisingly, we are doing slightly worse here with the statistical generation system. So instead of 0.244, it's 0.237. But still, we are able to improve on the baseline. Unfortunately, we don't have results on that system, but I guess it's a matter of running the system because formally the input is the same thing. Now for the input 3, we got the results like this morning. And remember, this is the automatically derived English improved by the information from the probe bank. And again, maybe not surprisingly, the number is very close to the previous two numbers because we are only improving the labeling near the verbs, right? So we actually made our lives slightly more difficult for the generation task, but we got approximately the same numbers. Again, the baseline had to be randomized because it was in the original work order. We didn't change that. So now the real translation. So here is the bad news. So first of all, for comparison, we are including the results of a GISA system that uses the results of the workshop 99 here, and of course it also uses the previous work done at IBM and elsewhere on a word-for-word translation system. And that has been worked by my student for the past 3 years. And this is the result for an English to Czech system that's based on lemmas on the Czech side and forms on the English side. And it uses a huge language model derived from 30 million words of American text. It uses a translation model built on every possible product text we have. So this is not a comparison, a competition to the system we have developed here because we are only using the Worcester Journal translations, but it's the state of the art in English to Czech translation. So I provide this number here. It's actually pretty high if I compare the blues, if it's ever comparable, but if I compare it to reported numbers for Chinese to English and other systems, so the number seems to be pretty good. Yes?
Well, it's also higher than what you got for the manual translations, isn't it? The 0.556.
But that's not quite comparable because here we are really going from Czech. So this number is actually very good because that manual English was derived from English. That has nothing to do with Czech.
Oh, okay.
So all the words in the input 2 are correct English words, whereas here you could get all kinds of junk depending on how it's trained. And
excuse me, I understood you to say that this is going from English to Czech.
no, this is going from Czech to English.
And what's on the right? 623.
Oh, I included another column here.
Right.
And it has something to do with the bad news I'm going to say. And I just want to
Oh,
improve
but
the impression.
did you say about something that is
I
from
guess-
English to Czech?
We don't have a real evaluation of
Then
English to Czech.
Then I misunderstood.
Actually, Jan was working on an English to Czech system for all the time, and he just did it for us, 2 weeks ago when he was here. And I believe that the numbers in the other direction are close, but probably not so close because of the Czech inflection problem. So we cannot go from English lemmas to Czech forms just by reversing the system because that would have too sparse data problems. So I would expect these numbers to be lower. Yes?
So what's 1G?
Okay, 1G, the blue score consists of 5 components. And it computes the unigram match, the bigram match, the trigram match, the 4gram match, and so-called derivative penalty. And the final score consists of all these 5 numbers. There's some formula for those. And the numbers I report here are the final numbers. But you can break it down to actually see what your system does. I have the printouts here with, there are huge amounts of numbers. But here, what I want to show is that the unigram match from the blue score for the GISA system is 0.62. So roughly it means 62% of the words that the system produced were actually found in the reference translations. Am I right? Okay. Now, for the same system, we actually did the baseline. Now, of course, the baseline doesn't have to be randomized because we can use the check work order, for example. That's what we did here. And the baseline comes out as 0.08 and 0.06 roughly. And that's again, just taking the dilemmas that were created by the translation from Czech and printing them out in the check work order. Now, what our system did slightly worse than the baseline here. And this is kind of puzzling, but I think from the last column I have at least some explanation. I mean, you have to understand these numbers came like in the last 2 days. We actually finished the system on Sunday. So we couldn't really look at the data. Actually, we do not want to look too much at the data because we would kind of compromise the data and that they are pretty expensive. So we will have to rerun the test on some other data to see what the system actually does. But I think here is one part. There is some explanation. The baseline got the unigrams only 0.48, right? We got the unigrams almost comparable to the Giza system. So what is hurting us must be the bigrams, trigrams, and 4grams. And actually the bigrams are comparable, and I look at the trigrams and 4grams, and they are much worse. And I believe it's because the word order model specifically is confused by some of the Czech words that were left from the translation and some other stuff, and the smoothing that's built into the word order model is simply not capable of handling that. So I think that's one of the reasons why the total blue score actually went down here. So, yes.
You say Giza, which model actually?
I mean, this is the best result. I mean, we asked for the best result, so it must be
5. Model 5.
Whatever I deleted. I think these are works up to model 3, and I believe this is model 3.
Model 3.
Yes.
Probably model 4.
But it could be.
I don't think that's released.
So, we don't know.
I mean, what I know that Jan works with the official Giza distribution plus the new version of the decoder. But since he works with the Giza distribution, I think it's model 3. But I will have to check.
The official meaning the thing that was finished in 99 workshop? Or
The one that was released slightly after the workshop. I don't know.
Giza plus plus.
It's Giza plus plus, yes.
Okay.
Then it's
Well,
4.
that has.
Then it could be 4.
Okay, but I don't have to check anyway. Just to be sure. No, I don't. And then we ran the same data through the existing system plus the transformation that Drago did, and actually, I mean, this number is still kind of hot, right? It's like 2 hours ago, and that number is really low. But we would have to. I mean, I have no explanation for that, but maybe Drago can say something. But this is kind of the bad result. We have to really look at the results if it's just the work order model and what can we do about that. Again, let me remind you that for all the evaluation, that I think we were hurt by the fact that the actual proposer was not in the system because, for example, we couldn't get any verb forms correct because we never proposed any auxiliary verb, for example, and we never proposed any conjunctions. So, you know, in this respect, I mean, it's now easy to do, but everything needs like a day or two to put it in, retrain it, and actually get the proposal in would also take about, my guess would be a couple of days to a week. And then, of course, we could propose everything, but, yeah.
For the about test for Argent, the training was done on input 1, which is automatic English TR, and it was tested on translated Chinglish, so it's very different. It has to be trained on Chinglish.
Okay, so now I should say something. Oops. No. Something at the end. So the good news is that we actually had a system working from end to end that was developed here at the workshop. I mean, for the generation part, all the components were done here, except for Dan Gilda's work on the model that was done. The first version we had even before the workshop. And for generating from the English semantic representation, we are doing better than the baseline, and that's significantly better, again, without the proposer in the system. And we have one of the results I think are kind of valuable from this workshop, that we actually have various resources for doing both generation and machine translation in place. They are checked, they are compatible, and they work. The bad news is that actually we still have to integrate the proposer into the system, and then of course that we have to look at the results why we couldn't beat the baseline on the actual system. So the things to do. Well, as I said, integrate the things that are missing. Try to write more classifiers like the preposition insertion, and of course integrate them into the system. That should help all the insertions. Do true EM smoothing for the smoothing part of the system. I mean EM estimation of the smoothing coefficients. Doing the smoothing is still kind of hard coding part. So we also would like to play with it more, like make a decorative system for breaking up the model into various smoothing distributions. In the aligner, some pruning has to be done, because once we go with the real proposer, it will suggest more possibilities, and the decoder will be slower than it's now. Of course, the smoothing issue I already talked about. We should also look at the non-terminal issue that would actually allow us to propagate information between the little trees. The little tree model is currently a joint model, so as Jason said, we should be able to incorporate a language model, because that would allow us to train on large amounts of data, which we actually prepared during the workshop. We have like 500,000 sentences parsed for building the tree language model. And then of course, we should do the same thing we did for the reverse check, for the check parsing, namely to initialize the first iteration of the EM parameter estimation by using the manual alignments that we have got only recently. And of course, we should try to incorporate transfer that actually goes to more, that actually doesn't give us only the most probable word, but give us several possibilities. We could also make use of the deep word order, which we currently don't do. We simply randomize the word order for the system, and of course run various experiments. Then of course the interesting thing here, since the tree-to-tree transduction model is a very general tool, we could try to do both parsing from AR to TR, and on both sides, like English and Czech. And also we can try surface translation, and of course we can try the translation on the TR, and possibly for other languages. We are building resources for Arabic now, and we hope to be able to do it hopefully within a year or so. Yes?
Well, this may be a question more for Kishore, but I'm thinking about the problem that the unigrams and the bigrams were okay, but the trigrams aren't. So if you've got a determiner or a preposition or some other function word every 2 or 3 words, and you've got either no determiner or the wrong determiner, or no preposition or the wrong preposition, is that going to totally screw up your trigrams?
Yes.
So it could be the proposer.
Yeah, it should be, but since for the English data we were able to do better than the baseline, there must be still some other problem here. This was the same system.
You didn't have the proposer for the English data.
Well, we had this basic proposer too. I mean, it was the same proposer that was used for the English data as was for the Czech data.
Okay.
So I suspect the word order that was kind of, thrown out of order because of so many bad words, or I don't know what was the reason. But it could be the proposer contributing to the problem as well, of course. Okay, so that's the end. But I hope that actually we have put together a team of people who worked on the same problem, and that we can continue working on various parts of the system to actually make it a coherent system. And you will also hear now from the 2 students in the proposals how they want to develop the system further. So I would like to ask Yuan first to present his proposal.
Good afternoon. It's me again. The title of my proposal is Machine Translation Based on Probabilistic Synchronous Dependency Insertion Grammar, which I call it PSD for short. The supervisors will be Martha Palmer and Rowan Joshi. First, the outline. First, I would like to address some issues that I observed in the implementation of the machine translation framework in the workshop, and then will be a proposal itself. We'll start with the machine translation framework that I'm proposing, and then will be something about the dependency insertion grammar, and then will be something about machine translation modeling, and then the decoding part. And I would like to address some technical issues that one might encounter if he wants to carry out this whole proposal. And finally, it's the allocation of currently available resources. First, some issues. First thing, after hearing our group's presentation, there's several reasonable questions that one might possibly ask. First, is TR, which is a technical grammatical representation, a good layer for representation for the language, or is it a good layer for translation? As you probably noticed, that TR is based on deep syntax. So the answer to the first question is probably yes. But what about the second question? Let's wait and see. Another issue is that, do we actually need a well-defined version of dependency grammar first before we actually launch the training? So, I mean, we first have a dependency grammar formalism. As you probably have seen in Jason Elsner's presentation, that before we actually launch the training, there's no specification for what exactly a dependency grammar should look like. We basically assume any subset of nodes can be matched to another subset of nodes. And currently, what we're implementing is not beyond the limit of 2 to 2. And the third thing is that, should we combine the different probabilities in dynamic programming decoding, which is to say, the lexic transfer, topology, and word order probabilities? Or can we combine all three probabilities in the decoding part, or we can combine maybe two of them? Okay, here's something that I observed from AR to TR annotation. For machine translation purposes, let's look at these two examples. First one is the apple is in a box, and the second one in 2001, the government issued blah, blah, blah. The two ins here in English is one means location and the other stands for indicate time. However, if they are translated into Chinese, say, they are going to be translated to the exact same expression pattern. But if we are doing AR to TR annotation, we must disambiguate whether these two ins indicate location or it indicate T1, which stands for time. Then, for machine translation purposes, this disambiguation is not necessary. So here is what I'm proposing. Sorry, it should be a line here. Instead of what the transfer that is currently being implemented in these summer workshop, I'm proposing to have the transfer from here to here, which is roughly at the AR level, instead of going deep to TR, do the transfer and go back to AR again. In other words, the proposal including two parts. First, to have machine translation based on shallow syntax level, which is roughly equivalent to AR, and I will explain in the future. And instead of a deep syntax level, which is TR. And the second thing is have a dependency insertion grammar definition of formalism first before we actually start training. Let's look at some possible strengths of this, what we might have for this proposed approach. First, as we have shown, it will reduce unnecessary disambiguation. And the second thing, as you probably have noticed, because there's no AR to TR annotation, so we could reduce the training data noise in this way. Because currently the AR to TR annotation is done automatically, and it's not guaranteed to be 100% correct. And it is obvious to see if we apply this approach, the whole translation pipeline will be significantly shorter. The original pipeline, which is currently implemented in the workshop, starts from some surface centers in Czech, goes to Czech AR, Czech TR, and Czechish TR, and then English TR, and then English AR, and then surface centers in English. So what I'm proposing is like this. It starts from surface centers in Czech, goes to Czech AR, directly go to English AR, and then goes to English service centers. And it is obvious to see that such a shorter pipeline means less noise accumulation in decoding phase. And by having a dependency insertion grammar, there's a very straightforward way to construct a generative model. And again, by having a grammar on the first hand, there's a way to estimate the probability for unseen data. I'll address these two issues later. So first, let's take a look at what is exactly a dependency insertion grammar. It is a well-defined mathematically rigorous generative version of dependency grammar. If compared against dependency trees, the dependency insertion grammar is actually doing this. Something similar, as Jason previously shown, is to breaking down the dependency tree into elementary trees with lexicalized or unlexicalized nodes. And the elementary trees constitute the basic elements of the grammar. The elementary trees are composed into a dependency tree, which in the Dick sense is actually a derived tree through unification operation. And further study can show that a dependency insertion grammar is weakly equivalent to context-free grammar and is strongly equivalent to tree insertion grammar, which is a variation of tree adjoining grammar, but with the condition that the tree can be only inserted either on the left-hand side or on the right side of the bigger tree. Okay, here's some example of how the dependency insertion grammar works. The first example is quite easy. It just shows how the adverb is adjoined to the verb. And we have the arrived at the dependency tree on the right-hand side. And the second example is quite complicated. Who does Mary claim Sarah likes? This sentence has a matrix clause, and it also has a embedded clause. And it involves WH movement, which has long been a problem for dependency grammars. As we know, WH movement will sometimes cause the so-called non-projectivity, which is to say, when you're actually having a dependency tree, you cannot walk through the dependency tree and having the correct word order. So such a problem can be handled gracefully by the dependency insertion grammar. Maybe you should notice the star here, which it basically means because it is a predictive adjunction, so the dependency patterns is actually reverted here. Well, I'll skip the technical details here, but we can see that on the resulting dependency tree on the right-hand side, there's actually a way of tree traversal algorithm which will generate the correct word order. Goes like who, goes down, down, does, and next child Mary, pop back to the parent, claim, and goes to Sarah, and go back to the root likes. And tree traversal algorithm generating the correct word order is quite important because it basically implies that for every element tree, we can store the word order rules locally, just based on the root of the elementary tree. So, why is this important to machine translation? Here comes the assumption. The assumption is the derivation tree of the dependency insertion grammar in both languages are isomorphic. Well, we must notice here, I'm not saying that the derived dependency trees themselves are isomorphic. I'm talking that the isomorphism actually lies in the derivation tree. So, given the isomorphism in derivation, it is obvious to see that we can have a synchronous grammar. The derivation trees may look like similar to the TR without semantics, if you want to put it this way. And so thus we have synchronous dependency insertion grammar. The idea is somewhat similar to synchronous tag. Okay, here's some possible strengths for this synchronous dependency insertion grammar. It can handle the structure variation and lemma variation in a formal and uniform way. And most important of all, we can construct very straightforwardly a generative model for it. And because it's a well-defined formalism, it's easier for machine learning, including parameterization and probability estimation. The probability, and I will just later that we can actually find a way to do probability estimation for unseen cases. Okay, here's how the synchronous dig look like. It's basically elementary tree pairs with the root of the elementary tree and non-lexicalized empty slot aligned on both languages. Here's just a simple English Chinese example which shows that synchronous dig can actually capture the lexical transfer, and here it shows that the synchronous dig can capture structural variation, with throw-out is actually being translated into one word in Chinese. Okay, now one step further, we can add probabilities into the synchronous dependency insertion grammar, which we finally arrive at PSD. There are basically two types of probabilities. First, it is the probability of how the elementary tree is unified in one language. And the other probability is what's the probability of the elementary tree transfer between the languages, which is, in other words, it is the probability of two elementary trees in two languages being paired. Now here comes the exciting part. It's the decoding and the generative model. As I mentioned, we can construct generative model very straightforwardly. And second of all, by having the conditional independence assumption, which is to say the derivation tree of the dependency insertion grammar actually represents the probability dependency graph. And thus, by having this assumption, we can have bi-turbid decoding, which I believe will capture both lexical transfer and topologies, which is a form of structural variation. And it is also doable to capture word order in the bi-turbid decoding part, or on the other hand, we can have a separate language model to capture word order. And most important of all, the whole decoding phase can actually be done in polynomial time. Now here is the illustration on how the bi-turbid decoding will work. ET here stands for elementary trees, and the dashed arrows depict conditional dependence. Well, by looking at let's examine the derivation trees on the left hand and on the right hand side. We notice that by assuming the two derivation trees are actually isomorphic, then we can draw the conditional dependence arrows like this. One might notice that this graph actually looks pretty much similar to the Markov model, whereas here on each side we have a tree. However, in the Markov model, on each side is a linear sequence. So by having this conditional independence assumption, we can actually construct the generative model in a very straightforward way based on the derivation tree of the PSD. Okay. The whole approach to implement the whole approach, there might be some technical issues that one will encounter. The first is how to build the dependency insertion grammar. Previously, there's a project being done at Penn called Extract, which is to learn the tree adjoint grammar from Penn Tree Bank. I believe that similar approaches can be done to learn the dependency insertion grammar, because actually it can be proved that dependency insertion grammar is equivalent to has strong equivalence to tree insertion grammar. And to learn the probability of monolingual dependency insertion grammar is easy. It can be done by observation. Here is a more difficult part. How to learn the probability of bilingual tree transfer in a PSD sense? Well, as you have seen in Jason Elsner's presentation, there's a EM algorithm for the observed pair of elementary trees. On the other hand, if you have defined the elementary trees in tree pairs, there's a way to estimate the probability of the unobserved elementary tree pairs by vectorization. I'll show later. Okay, here's now how the vectorization works. this graph shows the dependency frequency distribution of the elementary tree, ETI, in one language. And ETI has a the ETY is dependent on ETI, which with a frequency of 122 and blah, blah, blah. And from ET1 to ETN. From ET1 to ETN, it's all the other elementary trees in the same language, and we just count their dependency frequency. And then we can vectorize ETI in such a form. Each element of the vector actually represents what's the frequency of the elementary tree ETJ being dependent on ETI. Having vectorized every elementary tree in one language, there's a way to have probability estimation for unseen elementary tree pair. Let's assume that we have never seen ETI and ETI prime being paired in our training data. But given that we have vectorized ETI in language A and the ETI prime in language B, assume we can actually find the probability for pairs ET1, ET1 prime, ET2, ET2 prime to ETN, ETN prime. We can actually build a probability for ETI, ETI prime using some similar idea of vector, the distance between the two vectors. Actually, some similar approaches has been used in word-sensitive disambiguation. Okay, here is the allocation.
Are you about to conclude?
Yes.
Good.
Here is the allocation of currently available resources. I'm thinking of doing experiments in Chinese English machine translation, because the obvious reason is that I can understand both. We have Pentry Bank and Transistry Bank to learn the monolingual grammar, and the LTC has CE parallel corpus and bilingual lexicon, and Penn has developed a Chinese parser. There's no Chinese parser in English, and then Gilday has did an English language model for this workshop, and Christine Patton has the English morphology part, and we have the evaluation software Blue. And because NIST is currently carrying out the Chinese English machine translation evaluation every year, there's a released evaluation reference from NIST. Okay, so here's the conclusion. The whole pipeline is kind of optimized for machine translation, and I'm proposing a probabilistic synchronous dependency insertion grammar. And there's a straightforward way to construct generative model in this way. And we can actually do backup for unseen cases, and this whole thing features polynomial time decoding, and the resource is currently ready. Okay, and thank you.
Is the synchronous dependency grammar something that's in the literature, or is that your idea?
I believe there's no strictly defined synchronous dependency grammar before, but actually it is something similar to synchronous tree adjoint grammar. There's actually can be a deterministic conversion from tree insertion grammar, which if you can call it synchronous, say synchronous tree insertion grammar and goes to synchronous dependency grammar and go back. But it is not exactly equivalent to synchronous tag, because tree adjoint grammar is actually context sensitive. Any questions?
Okay, so the last presentation will be Martin Schmerik's proposal for the post-workshop work.
So the title of my proposal is three transducers tools for machine translation. It will be about integrating the tools we have developed so far into one distribution package. So what is the motivation for the project? Motivation is to take the model we have developed and test it in a big set of experiments in various deployment configurations. I would like also to evaluate it on more corpora, more than just on Pentry Bank parallel corpus. And this should help us to answer the question, how much information relevant to MT do AR and GR representation really contain? So here is our roadmap. Czech language, English language, surface text, analytic representation, tectogrammatic representation. This is what we have developed so far. There is a tectogrammatic to analytic transducer, generating transducer, which takes as input rule-based transfer. There is, of course, some AR to surface morphological to generation tool. So the first step would be to implement 3-to-3 transducers-based transfer. Train it on TR and TR parallel Czech English data. And train another transducer on its output and try whether it accommodates errors which are generated by statistical transfer. Or maybe we could try to do both two steps in one. The other possibility is to go directly from analytic representation to analytic representation in English. And lastly, we could also try to improve Czech parsing, the Czech analysis using 3-to-3 transducers. And these are our main competitors. I would like to test it not only on Entry Bank, which is still growing, the translations are still growing, but we have also 60,000 parallel sentences from Reader's Digest. This corpus was used in 99 workshop here. The problem is that translations are not very literal, and some parts of sentences are omitted during the translation. So it would be interesting to train, for example, the transfer module on Reader's Digest corpus so that we learn how these sentences should be reorganized, and to train the generation module on Entry Bank, our corpus. I would also like to go reverse direction from English to Czech. It would mean to improve tools generating, because now we won't have manually annotated data here, but for example, something like Collins parser, and so we will have to improve the scripts, the tools for AR and TR conversion. Maybe we could also use the 3-to-3 transducer. On the Czech side, on the generation side, we will face these problems. Czech has much larger text set, the morphology, it's program feature language, and we will have to handle these long distance dependencies. These are gaps to be filled. Okay. So in order to do these experiments, we will need a very modular toolkit. So the goal of the proposal is to implement this toolkit. So it should be very easy customizable and extensible, and it should contain also evaluation package and maybe some visualization, visual tools to see what's going on in the models. So how to do it? I would take the software we have developed so far and create distribution which would contain training package, decoding package, evaluation package. And so the system would be modular so that we can try, for example, different variants, different approaches to smoothing, maybe switch from a joint probabilistic model we use now to condition probabilistic model and incorporate language model into the whole system. We have definitely to implement and finish the proposer implementation. It would be nice if the proposal could have access to any information in the tree so that it could have, for example, these long distance dependencies. So this is just the training package in more detail. Well, I think There is one feature for large data set. It should enable to split the task into several jobs and then merge the results. And training, we should be able to switch between smoothing techniques and integrate the language model in it. Well, this is what I already said. We should be able to switch between several versions of proposal. There is also something to be done, implement pruning in decoder, and also parallelization in decoding phases. Well, and the third package, the evaluation package. Well, the core part will be the blue metrics system. It will evaluate like the overall performance from one to the other language, and it will also contain evaluation tools to evaluate like single components separately. For example, language model or different classifiers we use. So, just to summarize this proposal, we are going to develop a toolkit for 3-to-3 transducers with good evaluation package, with evaluation data, some visual tools, and we want to make it public available. And once we have finished this task, we can run these experiments I have proposed at the beginning of my talk. So, thank you.
I have one suggestion. Could you, if you make it publicly available, could you make it available under the BSP license?
Of course.
BNE license.
We have to discuss this. Yeah, I mean, we generally either do not make it public or make it public under the GNU license for various reasons. But of course, this can be negotiated. I mean, certainly even if it's developed under the GNU license, we are willing to give it under a different type of license on case by case basis.
The lesser GNU license?
Pardon?
Like the lesser GNU license?
Yeah. Or even a commercial license if someone wants the license. I mean, depending on that, we have to negotiate this on. Okay, so I guess we have some time for questions, and I'm happy to take any questions you might have. Yes, Dan.
So I recall that in the spring, there was some anxiety about whether the technogrammatical representations, as annotated, were reliable. And now that you've spent some time on this, I want to know your opinion.
You mean the manual annotation of the TR that's going on check? Yes, okay. I think so far it hasn't improved. So I think we are, in the annotation scheme, we are facing the same problems on a different level, but as we are facing with the actual translations. People have different solutions. It's not a performance problem. I mean, partially it's a performance problem, but it's a problem that people have different opinions what the semantics of a set of constructions. And it's not so much in the structure of the sentence as it is in the labeling scheme. Because formerly when we did the analytic level, or even if you look at the Venn bank, there are actually fewer functions that are being used for labeling. On the analytic level for check, we only have 6 major functions that could cause problems, and they are clearly defined. Here we have almost 70 functions, like time when,
70 or
70. So it's like 70, yeah. So all these time functions are very fine-grained, classified in a very fine-grained way. There are some default functions. Some people say this is not the default, this is the default. So I mean, we have to finish first a reasonable amount of data, and then we can actually run some significant tests on that. And after we have done that, we can possibly change the definition of the guidelines, or maybe not use some of the functions. But at the moment, the inter-annotator agreement rate is still below 90.
So, given that that's the case, it seems like a good experiment to run would be just to collapse a lot of the fine-grained distinctions into coarser distinctions and see if that helps your prediction accuracy.
Yeah, but I mean, we have to have the, this system actually in place in a way we can run it in an easy manner to actually try that, whether that helps or not.
No, but I mean, even on your subtasks, right?
Right, yes, yeah, okay. Actually, this will be part of the work on smoothing. I mean, there is still work to be done on smoothing, and that's actually the place where we will see whether the prediction from the functions to whatever we want to get, like the prepositions, is significantly different for 2 or 3 different functions. If it's not, then of course that's a good reason to collapse them. Other questions?
I want to say my 2 cents worth. I'm scheduled to tell you, to kind of review what has happened here, but maybe you certainly remember what happened here today. I could point out what happened yesterday to those who might not have been here yesterday, today. Who weren't here yesterday and who are here today. So we had 2 teams yesterday. One of them was speaker identification team, and they, by I should say by esoteric means, they obtained this great improvement from a standard way of doing speaker identification to this non-standard way. I'm not going to recite how it was done, but I think it's a considerable achievement. And then we had a presentation last time, yesterday, by the Arabic team, and they came to certain conclusions, which I'm not going to read for you, but here they are. Their results were an improvement, but not as dramatic as in the first instance. And today we had in the morning, we had talk on weekly supervised or semi-supervised training for statistical parsing and what you heard right now. I want to make 2 observations which I suppose could have been made at any of the workshops. Well, at least one of them at the last 5 workshops. I think it's about, I may be wrong about the figure 5, but since a certain time we've had here the undergraduate students, and I think maybe five years or something like that. And is this the 5th? All right, and I think this is just a splendid experience. Now, of course, they have to speak for themselves, but I'm sure that at least I could not recognize from the people who were presenting who was a graduate student and who was an undergraduate student. And I think most of them, or the vast majority of them, and that's true every year, don't come with a natural language processing or speech background, and we are able to bring them up to speed quite fast. Of course, they are elite students, but at the same time, I think this is a splendid way of educating young people. I've said it to my department chairman today at lunch, and I said that unfortunately this is quite expensive because you have all the other people who are here who contribute to this education. And his answer was, well, maybe education is simply expensive, and this is what you have to do if you want to educate people. So I think, I mean, I don't know how to duplicate this all over the world, but I think that a kind of a summer camp exists. There's summer camp in soccer and summer camps in skiing and summer camp in something, but we can have a summer camp in science, and I think we're very successful in it. So that's remark number 1. And remark number 2 is that lately globalization has been criticized, and people say what disadvantage it has. But certainly in science, globalization is with us and is enormously effective, and there is no distinction. We had 4 team leaders, 3 of them not from the United States. They all speak the same language, English, of course. But that's not what I'm referring to. I'm talking about how we approach sides and how we are able to, through cooperation, get great results. So this is the end of my remarks. Today, as you know, we're going to have the banquet, and also the people, the committee will consider very carefully the various proposals, and I think we'll come to some conclusion, and we will make those conclusions public at the banquet. Thank you very much for the splendid work you've done.